Welcome to Upstack America's IT training programs. My name is Bob and I'm the IT training lead for Upstack America. Today's training is on data science and specifically on artificial intelligence and machine learning. Our trainer will take us through today's session is Paul DeBacker. Paul is a data scientist with outstanding work experience managing digital transformation projects on artificial intelligence and machine learning. He also holds extensive experience as a solution architect for robotics process automation, and also he has experience as a developer for robotics process automation. Paul holds a Master of Science in Artificial Intelligence and Machine Learning from the University of Texas in Austin. He also holds a first-class honors Bachelor of Technology degree from Anna University, Chennai. Thank you for watching and we hope you will enjoy the training.
All right. So this week we're gonna be discussing two new algorithms. So we'll be splitting up it into two different sessions, right? So today's session we're gonna talk about is what is called as knife-based algorithm. Okay, and tomorrow's session we're gonna be continuing with KNN, which is a different algorithm, right? Okay, so let's get started with this. Right. So what is knife base exactly? Right. So what is knife base algorithm? What it exactly does, or how it is different, from different other algorithms that we have learned. So meanwhile, could you just highlight one thing, Kevin? I mean to say that. Like what we were discussing about certain algorithms, uh, yeah, so what we were discussing about certain algorithms is that uh, we understood that when we have built up a model, we have to prepare the data and we have to process things it in a different way, right? We have to make the data ready, and uh, and then it goes into the model, and then the model takes up the data, so it has to come up in a specific format and things like that, right? Now, when it comes to knife base, right, or any other algorithms apart from logistic regression. So when it's a regression kind of a problem, we know that we are in a numerical kind of a data. And then when we are into a classification problem, we know that we are talking about a classification problem where we are trying to handle certain amount of data and try to classify things, right? Now what happens with knife bases? So knife base is also a classification problem algorithm. Okay, so knife base, I think, yeah, if I was looking into the history part of it, so knife base is actually an classifier algorithm, right, which we call it generally. So knife based classification is a form of classification algorithm that relies on Bayes theorem. Okay, so Bayes theorem, or Bayes theorem, what we call in machine learning, is very popular. So when we talk about Gaussian, we talk about Bayesian. So Thomas Bayes is actually the person who is an English statistician, philosopher kind of a uh, person who has actually created this Bayes theorem that we are going to see in the upcoming slide. And this Bayes theorem which was developed initially by Thomas Bayes, is actually the ground rule for what we are trying to do for knife-based classification kind of a problem. So it's a classification technique that uses Bayes theorem, and Bayes theorem is completely based on probability. And we know what is probability. So probability in mathematics is nothing but the chance that a specific event might occur or might not occur, right? So I think in the very initial days of our statistics sessions, I spoke about a little bit on probability, and I did share you certain online links to go through and learn more about probability. So probability is a very, very crucial concept when it comes to knife Bayes, okay, or Bayes theorem, for example. Because in probability we have seen that, let's say if I toss a coin, right, I have two sides of a coin, one is head, another is tail, right? So if I toss a coin, the probability, so what are my maximum two occurrences can be either a head or a tail. So my maximum output of an event is two, right, in a when I toss a coin. And so let's say if I have coins, the front side, one side would be head, another side would be tail. So my maximum occurrence output is actually 2. Okay. Now, when it comes to probability, that if I ask you that, okay, Kevin, can you tell me that if I toss a coin, what is the probability that the output I'm going to get is head? Right. So what are you going to say? The total output probable occurrence of the event is 2, out of which head can be either head or it is a tail, right? So it can be any one of the event. So the probability of becoming head is 1 by 2. The probability of getting a tail is also 1 by 2. And always remember, the maximum probability that we can get is 1. Probability is never more than 1. That's how it is defined, right? So yeah, clear this out. Okay, so that's what we're gonna trying, that's what we are going to see here today. That probability of knife Bayes, or probability of Bayes theorem, how it is going to be applied, right? So probability would actually become a very, very important concept in our discussion today. So Bayes' theorem is actually the foundation of our knife-based classification algorithm, with an assumption of having prediction independent predictions. So if I tell it in a very simple way, knife-based classifier assumes that the presence of a particular feature in a class is unrelated to the presence of any other feature. So let's say when I have because all these are supervised kind of a machine learning algorithm, right? So I have my x's, along with that I have my specific y, right? I have my x's and I also have my y, which is supplied within the data, correct? Now, so what we are trying to say is, in knife Bayes we are trying to identify the presence of a particular feature in a class. So my y can have zeros. Let's say my y is a binary class. So in that case I will get either 0 or I'll get 1, right? If I'm trying to predict that, or if I'm trying to predict whether something is good or something is bad, right? So I have a specific probability in that case, correct? So now, when we are trying to do that, with knife Bayes, what happened? Yeah. So now let's say in knife Bayes, what we are generally trying to do as as a part of a classification problem is implementing the Bayes theorem, right? So now let's say, for example, I have given you an exercise that if you have a fruit and consider it to be an apple, right? So if it is red and round and about kind of a 3 inches diameter, you identify that, okay, this fruit becomes an apple. Now even if the features depend on each other, or on the existence of other feature, all of these properties independently contribute to the probability that that object is apple. Like, it is the round shape, it is the color, and it is the diameter of it, which is like, let's say, 3 inch. So all these attributes would also actually independently contributes from in terms of identifying that the fruit that you have shown me is actually an apple kind of a thing. So how does this exactly occur? How does Bayes theorem, works is, so I'm going to explain you that. Might be a little topic heavy or mathematics heavy, but yeah, you have to go back and read more about probability if it is kind of, a little tough for understanding and things like that. So Bayes theorem says that, it actually provides you a way of calculating something called as, we generally call it in statistics as posterior probability. What we call it as, we call it as posterior probability that we want to identify. Okay, so now what it says is, let's say I haven't, this is completely probability. So what is probability of a by b in probability, that you have to already know. So probability of a by b means that I'm trying to say that the event a is gonna occur with respect to the event b. So there are concepts like mutually exclusive, mutually dependent, and things like that. So we, how do we read it in probability? We read it as p of a given b. Okay, this bar is read as given. That means if, which represents that the probability of a, what is the probability of a if b was known to have occurred? That's how we read it in probability. That if I'm trying to find the probability of an event a knowing that b has already happened, that's how the meaning is. Now in many situations we'd like to understand that what is the relation between this p of b by a by b and p of b by a. There are some probabilistic differences also that we generally do. Now what it says in Bayes' theorem, the formula how it looks like is, it says that the probability of p of a given b is equal to the probability of b given a multiplied by probability of A divided by probability of B. Now this portion of the theorem, okay, is called as posterior probability. Okay, this portion of the theorem is called as posterior probability. We try to identify that what would be the probability of A given that the event B has already occurred or B is already known, right? Now, what is the probability of B by A? This we call it as, I'm not going too much deep. I'll explain. I'm trying to be as generic as possible so that you understand. So this probability B by A is called as likelihood probability. Okay. This probability P of A, we call it as prior probability. Okay. We call it as prior probability, and this probability P by B, we call it as predictor prior probability. Okay, we call it as predictor prior probability. So generally P of A by B, which is my posterior probability, is actually my target class in any sort of my knife based algorithm. Okay, P of A, what we are talking about, the class prior probability, is the probability of the uh, of the prior probability of my event P of A. P of B by A is my likelihood, and P of B is actually the predictor probability. So all these are associated pretty much with each other. Now this might be a little heavy, but let me quickly jump into the next real-time example, that how exactly this happens. So now let's say, so this is the back end of a knife based classification, because we don't have to do these calculations manually, because we know that we have the algorithm which would be available in as a part of our scikit-learn package. And there we will be discuss that package will be automatically helping us to kind of decide uh, all these parameters when we create the model. Okay, so now in terms of knife base, let's say I have been given an example that these are my parameters of the weather. Okay, and I am in a decision mode that whether I'm going to play golf or not. So what the data kind of is given to me is that when the atmosphere is generally called as outlook, let's say that this actually you can call it as the climate or the atmospheric condition, the temperature, the humidity, and the what is this nature of the wind. So this data says that when the outlook or the atmosphere is rainy, the temperature is hot, the humidity is high, and windy is false, that means it is not windy, I do not prefer to play golf. Okay. Then when it is rainy, hot, high, and the wind is there, still I don't prefer to play golf. When the temperature is overcast, hot, high, humidity is high, and windy is not there, it's not windy, I prefer to play golf. So like this, I have my various conditions of whether should I play or what. I mean, what if this condition of the day I choose not to play? If the day is like this, I choose not to play. Okay. If the day is like this, I choose to play. If the day is sunny, mild is the temperature, high is humidity, and not windy, I again prefer to play. So like this, for not playing and for playing, I have various predefined history, that on which day I have decided to play and on which day I did not play, and what was the exact attribute of my x's. So obviously we know that this play golf is my y, which is my target column, and these are all my x's, x1, x2, x3, x4, which decides. So now if I have, let's say this data I have noted over a week, that when I played, what was the condition, when I did not play, what was the condition, and it's my self assessment. I have written this theoretically on a daily life experience. Now let's say, so how many entries do we have here? It's almost like 1 2 3 4 5 6 7 8 9 10 11 12 13, let's say 13 to 14 entries I have. Now let's say after this, after noting all these entries on a, let's say 13 to 14 days, on the next day I wanted to identify or create a model or do a probability that okay, on this historical way how I have played and how I have not played, now if I have a temperature or a body or a rain outlook as, let's say, sunny, the temperature is cool, humidity is normal, windy is true, what does my historical data say, that what is the probability of my playing golf and of my not playing golf? So if I take this entry, which is, let's say this entry was still to yesterday and today was this condition. So this many observations I've manually done over my experience. Now I'm trying to create a model to predict it for me. I don't want myself to decide. I want to say that, okay, based on whatever I have done on the historical period of last 14, 15 days, I want the model to tell me that if this is the condition, let's say this is a very small record, let's say you have recorded for 2 months, it's not possible for you to remember, which date you played and what was the overall condition, right? So you want to create a model out of it, that okay, on my historical data, if any of the scenario repeat, I have a new scenario or any matching similarity of a scenario, should I play or should I not play? What does the model tells me? So this is where your probabilistic feature analysis, when analysis comes, knife based algorithm or classification becomes very effective, which in turn at the back end uses Bayes theorem. Okay. Now, the first step to kind of implement a Bayes theorem is, we know that we have understood that we have to find the probability of A given B, which is equal to nothing but probability of B given A multiplied by probability of A divided by probability of B. That was what we learned just in the previous slide. But now, so to do Bayes theorem, I cannot take so just for an understanding purpose how it exactly works, we took a cut of this data. And the first step to do a naive Bayes theorem, mathematically, like if you want to calculate by yourself with a small amount of data, the first thing that you need to do is to create a frequency table. Okay. Frequency table taking certain attributes. So what I did here is, I took a frequency, I wanted to create a frequency table with parameters. So I know that I have my outlook is one of the atmospheric condition. Then under outlook, I have how many different types. I have rainy as one category, overcast as one category, and sunny as one category. So under my outlook, I have three unique categories. So in frequency table, I took the outlook as an attribute and mentioned all the three different unique categories. If I would have had XYZ categories, I would have added it here, right? Now, I took my target column, which is which is my y, and I know that I have two unique variables in my y, which is either a yes, I play, either a no, I do not play, right? So I took this yes and no. Now what I did is I want to calculate the frequency table first, so that out of this frequency table I can convert it into a likelihood table in terms of probability, and then see what exactly was happening to my uh, what exactly is the probability saying me that whether should I play or not. Okay. Now in this frequency, what I did is, when the temperature is outlook is sunny, so let's say sunny, okay, I took all the sunny, and I took a count of yes, that when outlook was sunny, how many times I played. So when the outlook was sunny, I played once, I played two, and I think I played three, right? So see, under yes, when it was sunny, I have the count as 3. Similarly, when it was sunny, how many days I did not play? When it was sunny and the output of my playing golf was no. This is 1 and this is 1, right? See, the count is 2 here. So like this, I got the frequency of overcast also, and I got the frequency for my rainy atmosphere as well. So that's why it is called a frequency table, because for each of the outlook occurrence, I have calculated the frequency of how many times I have played and how many times I did not play. Got it? Now, to calculate or to convert this frequency table into a likelihood table, I need just to do a conversion of my numerical data into a probabilistic data. So what I did here is similar table. I just added one more column to calculate my row wise probability and my column wise probability. This is how it works. Okay. Now, when it was sunny and it was yes. So when it was sunny, my probability, my count was 3 that I played, and overall count of my when I played is how much? 3 plus 4 plus 2, right? 3 plus 4 plus 2 is how much? 9. So when it was sunny, I know that I played only 3 days, and overall days I have played was 3 plus 4 plus 2, 9. So if I have to identify that what is the probability that I play when the atmosphere is sunny, is nothing but 3 by 9. So 3 is the count of when I played, and my overall count when I played, irrespective of sunny or overcast or rain, is 9. So my probability here for yes when I play in a sunny day is 3 by 9. Next, similarly, I do it for the no column. So I played 3, I did not play was 2, and then here it is 3. So column count for my no is 5. That means for 5 days I did not play. Now, for 5 days I did not play, but when it was sunny, I did not play for 2 days. So what is the probability for me? It is 2 by 5. Like this, I calculated for overcast, I calculated for rainy as well. So rainy I played 4, but my 4 divided by 4 by 9, because my column probability of playing on irrespective of any sunny or any specific day is 9, right? I did not play. Overcast means I do not have any day where I have not played. Means in overcast day I would have mostly played. So it is 0 by 5. Similarly, I did it for rainy. Now I counted the probability for each occurrence of yes and no, and then I did a total of my column and total of my row. So if I add all this, right? So if I add the top part, like 3 plus 4 is how much? 7 plus 2, 9, and my lower and this denominator. So here I get 14, 9 by 14, 5 by 14. Okay. Here I also get, a kind of a total 5 by 14, 4 by 14, and 5 by 14. Now, out of this likelihood table, if I want to calculate my P of, so this is my posterior, right? As I showed here, P of A by B. So here it is mentioned as P of C by X. So C by X means what? Probability of when I played is yes, and the day was sunny. So I get a probability out of here, which is like this. Now, how did I calculate this? So first, to calculate c by x, I also should know x by c, and I also should know p of x and p of c, right? Like this is my p of b by a, okay? This is my p of a, and this is my p of b. And then when I apply this in the back previous formula, I get my posterior probability p of c by x. So let me clear this out. So now what I did here is I did P of x by c. That means the probability when it was sunny and I played, it is 3 by 9, which is 0.33. And what is the probability of P of x? P of x is nothing but only sunny. So when it was only sunny and I did not, sorry, yeah, when it was only sunny, I know the row count as 5 by 14, which is 0.36. And when what is my P of C? That means yes, the overall yes is, I know it is 9 by 14. So I took 9 by 14, which is 0.64. Now I know the formula. So for P of C by X, what I do is I do P of this one multiplied by this one divided by this one. Then I get a probability of zero point 0.6, which is, let's say, 60%. So now I can say that when the temperature is sunny, sorry, when the atmosphere is sunny and I want to play, I have a probability of 60%. And this is based on my historical data, what I generally analyzed over the past few weeks. So this is a little mathematical shabby, right? And you have to go and really understand the nuances of probability calculation in this case, else it will become a very little tougher. But this is how, Bayer's theorem or works at the back end of creating posterior probability of a specific event to occur when I know that the other event has already occurred. Like what is the probability that I'm going to play when the outlook is sunny, right? So something like this. Now, when I go on to the knife-based classifiers, so this is what Bayes theorem, and this is what this work utilizes. So knife-based generally utilizes the Bayes theorem, which we just saw. Okay, yeah, and then we'll jump onto the Jupyter. So what are the various attributes of my knife-based classifier? It's a probabilistic model. We have just understood that it's a probabilistic model which understands Bayes theorem. It is called, why do we call it as naive? Due to the assumption that the feature in the dataset are mutually independent. Actually, this is a probabilistic term, mutually independent. So this you have to understand, or what happens when an event is mutually independent. Okay. Then in real world, independence assumption is often violated, but knife-based classifiers still tend to perform it very well. These are some very statistical, statement in order to justify what are the attributes or my features of a knife-based classifier. The idea is to factor all available evidences in the form of a prediction into my knife-based rule to obtain more accurate probability of a class prediction, right? So this is what we have understood. And probably, when we jump onto the Jupyter notebook, we will be able to understand that, what exactly knife-based utilizes as a part of Bayes' theorem, and how do we just, plug and play this as a part of our model building. So, any questions on this? I know it's a little mathematically, statistically, little heavier on the side. But did you get the gist out of it? Like what exactly the probability occurrence means here, Kevin?
Yeah, I understood the probability part of it.
Right. Okay. So, anyways, with this, I've already shared you certain links of probability functions and mutually exclusive, mutually independent. So you have to kind of do your background research, in terms of understanding this concept. So ensure you go through those links and understand the basic ground rules of probability. What is mutually independent? What is mutually dependent? Target exclusive, and all those things. And then when you kind of revisit this, it will become more clear to you. And anyways, we don't go into the theoretical, we don't deep dive much into the theoretical side of it, correct? But what happens is, we have to kind of understand that how does naive base works, because when you develop a model, okay, when you develop a model, it doesn't mean that you have to, I mean, you don't have to understand the background concept. You have to understand the background concept, though you are not going to calculate it by yourself. But still, if you don't know that what knife base uses at the background and what sort of probability calculation it is trying to define me at the back end, it becomes very, very tough. In that case, you won't be able to analyze that, what is the model outcome. Now, let's take a quick deep dive into the knife base algorithm. So here we're going to discuss about knife based algorithm, where we are trying to say we have taken a data which is a income prediction on a census data. Okay, so it's a census data which was shared publicly available, where they are trying to do an income prediction. So what is the objective here? So see, this is again, so if you see the type of use cases we are dealing with, it's very different. We started with the cardiovascular data, which is of healthcare. Then we came into the, sorry, it was kind of a fitness kind of a data set. Then we saw one more, which was, I think, the last couple of examples, we saw certain variations and applicability in terms of different industry. And I think the logistic regression use case we were trying to see was on a diabetes data set, correct, which is a kind of a very much important or a crucial aspect in terms of your medical science domain. Now this is again into the income prediction, which is, let's say, generally taken or undergone by the financial institution of banks. So banking or fintech is the domain where this sort of exercises happens. So domain wise, it's a different sector for me. Right now, with respect to the objective, we are trying to identify, or we are trying to predict whether the income exceeds 50K per year based on the census data. Okay, so we are probably trying to identify that what section of the people have an income, or what section of the people have their income which, let's say, exceeds 50K dollar per year based on this data. I mean, irrespective of any currency, I think currency is not the factor here, but let's say we go by the value 50K. Now we have been given various attributes in the data, right? So the variable descriptions we have been given something called as age, which is a continuous data. We have been given work class, like what is the genre of your job? Like, are you in private? Are you a self-employee? Are you a self-employee in your own organization? You are a federal government employee, local government employee, state government employee. You are not earning without pay, or you haven't never worked. So these are my different attributes in my work class column. Then another what they have given is FNLWGT. So let me see what exactly was that. Probably have to look for this here. I'll check for this definition. They have given it as a continuous variable. Then they have given us the education background. So are you a bachelor's, some college grad, you are a 10th or 11th grad pass out, you are a professor in a school, you are an academician, you are, let's say, of 9th, 10th, 12th grade, or you have only studied till, let's say, the 4th grade or something like that, you are a doctorate, or you have gone to preschool, whatever. Different types of variations I have in my data. Education number is something given, which is again a continuous. What is my marital status? Whether I'm married with the spouse, whether an individual is divorced, never married, separated, widowed, married spouse absent, married AF spouse. So these are my different marital status variations that I have. Occupation. So what domain do you belong to? Whether you are a tech support guy, you are a craft repairer, you are into other service, you are into sales, blah 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 blah. You are handlers or cleaning, you are into machine inspection, you are into administrator clerk, you are a farming or fishing kind of a farmer, you are into the transport, you are into armed forces. These are the different types of occupation I have. Relationship, right? If this is an individual's data, right, what is the relationship of that individual with some other kind of a thing? So whether you are in wife, you are an own child, husband, not in family, you are kind of an other related, or you are unmarried. Race. Okay, pretty good. So what is the race they have given? It's a kind of, I mean, it's white, Asian Pacific Islander, American Indian Eskimo, different types. This is a census data, so I think they will have a variation in terms of the race and other things. Gender or sex, male or female. Capital gain, which is kind of a business domain. Sorry, banking domain, kind of an attribute. Capital gain and capital loss. This happens, let's say, when you on a banking domain, when you kind of invest somewhere, you get a certain profit, right? So In that case, capital gain and capital loss are those kind of a attribute when you kind of, let's say, do a share market business or things like that, or you have other incomes, those sort of a banking criteria. Then hours per week is continuous again. Sorry, hours per week. So how many hours do you work, right? And then what is your native country? I mean, this is self-explanatory, and I have this much variations of countries in this. And my class is a binary here. So I'm going to do a classification problem with a binary class. So I have two types of values in my y. One is less than 50k, and another is greater than equal to 50k, right? So either I belong to this class or I belong to this class. That's what we are trying to identify here. Now, uh, so this is all about the data and what was exactly given to us, right? And then we are trying to identify this. So we are going to say, we are going to import all our libraries, right? So we have imported NumPy, pandas. So here we are going to do some sort of an imputation. We know what is an imputation is. We have heard about level encoding, one hot encoding, and other things, because we have a lot of categorical data, right? These are my categorical values, so I need to encode them because machine learning would not understand what is United States. So probably I have to encode it with a label encoding like 1 or 0 or something like that. Then I've imported all my necessary pre-processing is one of my package. Train test split we already know. So here upfront I have calculated, or I have called all the libraries, so that I don't have to use or call my required libraries at the bottom whenever I'm programming. This is a best practice. So I have here called knife base. See, so the model we are going to use is Gaussian knife base classifier. That's what we were discussing. So how do we do it? So from sklearn.knife underscore base import Gaussian knife base. Okay. So in knife base also, I mean, we have a lot of variations, I guess, but the one we are trying to do today is a Gaussian knife base theorem. So under sklearn, you get to learn different types of, you have a knife base classifier, which we are going to use today, right? Okay. Now, sklearn.metrics import accuracy score. This is one of the way how we evaluate our model, right? We know that accuracy is our one of the parameter. So this is the data that I'm loading here. So I just named it as adult underscore df pd.read csv. I'm loading this. Now this data that was given to me is actually not an Excel file, not a typical MS Excel kind of a data where I have XLSX or XLSB format. It was given with a different format called dot data. Okay. So to read this, I used read CSV, but data files are also have data with a delimiter. Okay. And the delimiter here is asterisk. Okay. So probably in the data, I'll see if I have the raw data file. So in that case, each attribute or each row is actually splitted by a asterisk kind of a thing. Like in CSV, what we have is comma separated values, right? Like this here also in data, my delimiter was asterisk. So I'm using delimiter is equal to asterisk. I don't have an header column, and I'm saying engine is equal to Python. So with this command, I'm able to read this data file from this dot data extension. Now we have loaded the data set. It is saying, I mean, that's what I was telling, that it is observed that the file extension is dot data. So we are passing some parameters to read this data file, which is delimiter strict, and then we are getting the data loaded. Now what I did here is I just did my data frame dot columns to understand that what are the, how the data was read. See, since I was not having the data in an Excel kind of a format, the data columns was not present, but when I read the data, it kind of made an columns like 0, 1, 2, 3, 4, 5, 6 till 11 based on all these features that were available. But with this 1, 2, 3, 4 column name or header name, it is very tough for me to understand what's going on, like what are the attributes I'm dealing with. So this is also a different way of handling. So what I did, I know that these are my columns which is available to me in this pattern. This is the hierarchy. So what I did, I took adult columns and I created a list, and I manually inserted all the names that I know for all these possible 14, 15 columns. Then I did, so what happens is now I have updated this list with this name. So adding headers to the data frame. So when I got this adult.columns, I know these are the numbers. I said, okay, update it with columns, and I passed on the name. So then when I saw the length of the data, okay, I see that I have 32,526, like 32k plus kind of a number of rows that I have in my data. I checked if there are any null values. Is null dot sum? It says none of my attribute have a null value, which is good. I don't have to do any fill any. Correct. Now let's try to test whether any categorical values. So what we are trying to do here is, since we have a categorical value in the data, okay, now we wanted to check that whether are there any, kind of incorrect symbols or signs, like, question mark. And since the data is not in Excel format, we are not able to view the data properly in an Excel. It's a data file. So we wanted to check that are there any categorical irregularities in the data. So what we did here is, let's try to test whether any categorical data contains question mark in it or not. So at times there are question marks or empty spaces in place of missing values. Okay. Using the below code snippet, we are going to test whether this data frame consists of any categorical values with question mark. So what I did, I just ran a loop. I said that for value in this entire list, where I passed only the categorical columns, because I know that certain columns are continuous. Like this column, my number of education, this I don't have to pass because these are all numbers, right? So I passed on only the categorical columns, and I wanted to say print the value sum of this where you find this symbol. So it says that in your work class you have 1836 such values where you have this question mark. In native country you have 583 values, but other categories does not have it. So the output of the above code snippet shows that these many values here and this many values here have missing values. Now what happened here is, when I did is NA as null, why you might have a question that, Paul, why it did not show me that I have a missing value here. Missing value is null always detects that if that row is empty or not, then only is null captures. Now in terms of age, let's say in the age column I have age for all the people, but in one column I have given, in terms of without any age, I have given a number. So let's say generally what happens is, why it did not capture in is null. So when is null has checked this age column, it knows that it's a categorical, sorry, it's a numerical column. So it should have values like 20, 25, 26, 30, like that, right? Then when it checked, it found that all the columns have some value. Now what is null does is, so let's say if in any of the age column, I have something like this, okay, which is a incorrect data for me, right? This data does not make sense, but is null will not capture this because it is not an empty or a null value for him. Is null checks whether there are value available or not. So if it is completely empty, then it would have given me that, okay, you have 20 empty values in your age column in the data, but it does not check my variability in the data. Let's say in the education column, I have 20 different types of education. Some education has come with like this. There are no values to it, but only question mark. So what is null does is, when is null checks, it finds some string in the data, right? Then it does not return me the count. So when you are dealing with categorical data, remember one thing out of experience, in any machine learning exercise, when you are having categorical data, it's a pain for you. Categorical data where you have strings and other things, you will always have to be extra cautious in terms of handling them, because they might have variations, errors, because free text or strings can have anything, whereas it is easy to handle numerical data in data frame. Okay, so now we just did the basic EDA here. We just copied the data frame into another data frame. First we did a describe, which we all know. We wanted to see what are the variations in my numerical columns. So if I say age, so mean average age in my data is 38, standard deviation is 13, and I have got the minimum percentile or quantile values. Similarly, I found every other aspect in the data, what is the mean, standard deviation, by using describe. Now, in terms of data imputation, so wherever I have a categorical value and I have a question mark, I need to replace them, right? My model will not treat them as a accurate data. So what I did is, for all these categorical columns, okay, I said replace value is equal to adult. This is my data frame dot describe, and then I'm trying to identify that wherever you find this value, go and replace it with the value which is available at the second index. Some sort of an imputation has been done here. So what it says is, for knife base we need to convert all the data values in one format. We are going to encode using labels from 0 till n minus 1 classes. So that means we are going to label encode all my data, and for implementing this we are going to use a label encoder in our scikit-learn. So we know about label encoding, so we called pre-processing.label encoder, and I have passed all the columns of my category wherever I need to label encode it between 0 and 1. And then when I see my data, so most of the categorical column gets label encoded. Now certain columns I have, we are now trying to create some dummy fields. So we are dropping some of the categories here, drop old categorical columns from the data frame. So this is one of the practice. So what happens here is, some of the categorical columns, after we have identified something, so we are trying to kind of drop here and re-index them properly. So we dropped them, but what we did is we created an one hot encoding, because we are adding some dummy fields. And we know that for one hot encoding, what happens? We passed on the data frame with a which is there with the column with respect to the column, and we did an one hot encoding of the entire columns. Right now, whatever my categorical data was there, see, it got converted into numerical values. Right, so we have created multiple categorical columns, so it added some columns for me. Right, so and then when I see, my data got actually transformed. Now I did a slicing where I created my X and I created my Y. So what does that mean? So I know my target column is this income. So see, I have taken 0 to 14, which is my all X's, and I've dropped and I've taken for my Y the only 14th column. Right, so this way I have 14 X's and I have only one target column. I do a test and train split here. Okay, and I'm calling the model CLF is equal to Gaussian knife base, and I'm doing a fit of my X train and Y train. These are all very similar to what generally happens in a machine learning model. So we are using a knife based classifier, which is kind of what we are trying to do here, and we did fitting, and we just did y predict is equal to x test, and we're trying to see what is accuracy. So my model just gave me a 79% accuracy. So now after this, because I did not want to kind of go too much deep here, because you have to understand this transformation, but just to show you that this portion, so always remember that from model building, it's very, very easy kind of a task in machine learning, right? Because once you have your data ready, you know that you will create XY, you will call the model, you will fit the model, you will do a prediction, you get the accuracy, and then you will print all your Y predict and Y actual, and you can find the variation. This data model building is similar for all the machine learning exercises that you do, irrespective of any data set. But what is challenging for a data scientist is this EDA top portion, plus how do you transform the data. And this does not happen in one iteration, let me tell you honestly. Never ever you can handle much categorical value with one iteration. You might have to go through 4 or 5 iteration of data pre-processing to understand the data, to remove out all the nuances, the noises in the data, and take the perfect cut. Okay, now as a data scientist, let's say here I have been given, what's the shape, what was the shape of my data here? It was around 32,000. Now I know 32,000 is still a very less data for a model to understand, I mean generically, if you understand, if you say, right? But if this 32,000 data is given to me, which has a lot of noise and nuances to it, it is me as a data scientist who has to decide that what is this perfect cut of the data from this 32,000 data that I should take into the model. Because the more I take unnecessary data, and see, this is a direct practice, that's why you are seeing everything at one shot. But when we did this, we kind of gone through multiple iterations and saw what is the best fit. We've also, so categorical column will always give you that challenge. You will not be able to understand the nature of the categorical columns of the feature at a very single shot. So you have to go through multiple iterations and take certain tasks and see what the data exactly has called in, you know. So that's the reason, till this model building will be always similar, any of the exercises that you do or I'm going to share upfront in upcoming sessions. But remember that when you do the EDA, create the data and transform the data, It is you as a data scientist who has to understand that what is the right data for me. How do I remove noise? What are the columns should I drop? What are the columns I should take forward? Not everything that is given to you is 100% accurate for your model. And there are various other parameters to, decide which are the target columns that is impacting, sorry, which are the independent columns or axes that is impacting my target column, you know. So in those scenarios, it is your data scientist capability or skill or experience or expertise that comes handy. That's why the data scientists, it is called as data scientists, because you research on the data and you are the solely responsible person that if you are building a model, and let's say I take 32,000 data and I say no, I see only 15,000 data is suitable for my model building and rest is noise. I remove it. But you as a data scientist have to be self-convinced, either statistically or machine learning concept wise, and you should be able to justify why did you drop those columns. Now sometimes what happens is when we go for review with, let's say, any higher technical authorities, and when the model goes into production, they want to understand that why you dropped this segment of the data. Then I have to tell them that, see, I did this kind of EDA which gave me this kind of an output, but what I understand is, per my experience or expertise, is that this portion of this 15,000 data is what is making my model describe, and the remaining data is noise for me. So that's why I've cut down. So taking noise with the data, and quote and carefully quote this line: taking unwanted or noise with the data, creating a model and getting 90% accuracy is is not at all an effective data scientist. If you are taking a proper cut of the data, let's say even with 50% what was given to you, with all the strongly correlated x independent columns that defines your y, you go into the model and build it and you get 60% accuracy, that will be much more appreciated or acceptable in a production. Because when your model is 90% accurate with a lot of noise, that means you have overfitted the model. Like, we know what is overfit and what is underfit. So your model at a future perspective will start making bad predictions because you did not cover all the different scenarios that the data could see in that specific domain. So even if I have this census data of predicting income, so let's say what are the columns given to me, 1 month later they add two more columns into the data, obviously my model is going to fail, because whatever pre-processing I did, those two columns were not available as a part of my older data given to me. And that model will find those two attributes as pretty new, and programmatically also Python will throw you an error before it goes to the model, because when Python runs your data on a code on a new data, those two columns will not be available because it was not there and you haven't created those pre-processing labels, right? So Python itself is going to upfront give you an error. So those are the scenarios also there. So what we generally do is we take those columns which are frequently coming in the data, and any unwanted column will eventually be dropped. So this is how exactly it works. Any questions on this, Kevin? Or you will understand what I'm trying to explain in terms of the sincerity of the data, that you have to kind of build in or you have to kind of generate.
Yeah, yeah, I see. I follow what you're saying. I'm just saying there's a lot of cleaning up you gotta do with your categories.
See, I will probably, once you're once we go into the exercises, and let's say once you complete, I'll show you some data. Now it will be a little very tough for you once you understand all the concept. I'll show you data that are as worst as possible, and by the worst I means unstructured data. I have seen data where ages are given not in numbers but in brackets. I mean in ranges. That this person age ranges between 35 to 45. Now how do you take those range as a parameter in age column and handle it? This is completely unstructured. Now 35 to 45, what your model should understand? You know, if your model takes the age as 35 and actually the prediction is based on 35 but inaccurate, but in real time let's say the person's age was towards the upper threshold, then I've added unwanted or unknown error to my model, right? So those are the things. So what generally we do is, in those range based columns, We try to calculate the quantile values that we saw in a box plot. 20%, 25% quantile, 50% quantile, 75% quantile, 100% quantile. Once we calculate the quantile values, we go and see that, okay, within my 25% quantile, what are the values that are falling? What's the, that value we go and impute. So like this, there are, different measures. That's what I always say, that nothing is wrong in data science unless and until you're able to justify your logic, you are good. With the statistical knowledge and machine learning knowledge, whatever you do, and honestly, you'll see when you get into a lot of machine learning, hackathons or other things, I'll show you in upcoming days. One exercise given to five data scientists have done it in five unique ways, because everybody thinks in a different way. That's why there is no hard and fast rule in data scientist. I have solved this problem with knife base, for example, for the sake of explaining you with this algorithm. Someone would have used a linear regression or a logistic regression kind of an algorithm, and you would have done much better. So that's why there are provisions that, there is something called as trial and error. So one data set, when the data is processed, we apply 4 or 5 algorithms. Like we know that knife based, logistic, these are all good classification algorithms. When I have a classification algorithm handy, I cannot just, bluntly say that, okay, logistic regression would fit here, unless you are so experienced and you know each and in and out about logistic regression, that by seeing the data you decide that, okay, I don't want to try anything because this data fits properly into the logistic regression. That's your expertise. You're brilliant. But generally what we do, we take trial and error methods. We try 2, 3 models on a specific data set and see which model is giving me a better outcome, which outcome is making sense to me, and which outcome of my model would actually run in a production environment, which outcome of the model will cover maximum or majority of my data set, and give me a better prediction. So something like this. So these are the conceptual things that goes in, right? So you have to spend some time and understand, because these exercises that we're going to see will be a little heavier on the statistical side, or let's say mathematically. So when we talk about knn tomorrow, we will talk about distance calculation. you know Whatever we have learned in mathematics, you have different types of ways to calculate distance. So knn is a different, we call it as k nearest neighbor, which creates clusters. So these are all various attributes, different angles of seeing the data. You create a probabilistic feature, you create out a clustering feature, you create out a linear regression feature. These are the various types that you can apply on a specific classification problem. All right, so I think, yeah. So any questions, Kevin? For, I think, yeah, we are pretty much on time.
Not really, but
All right. Yeah.
could you you'll upload this deck after the session, right?
Oh yeah, yeah. I'll pass it on to Bob, so that he can share it to you.
Yeah, I'd like to go through it.
Yeah, definitely. So what I'm gonna